Hello physics students, this is Dr. Brenzi and this is lesson 8.1.1 for advanced physics. We are starting a brand new unit and our unit is going to be about electricity. Our objective for this lesson is that we're going to be able to compare and contrast the gravitational force with the electric force. I want to start by showing you a little simulation here on my computer. It kind of simulates something that maybe you have done in real life here. And what I can do in this simulation is I can take a real balloon here and I can move it around. And if I rub it up against this, well actually before I rub it up against a sweater, I'll just show you that I can move it and then I can let go of it. And the balloon just kind of stays where it wants to stay, doesn't do anything special. But something interesting happens when I rub this thing on this sweater here. Now, if I let this balloon go, interesting, it's attracted to the sweater. Okay, so there's some strange force that I somehow made by rubbing this balloon on this sweater. And what's even weirder than that is if I decide to push it against this wall here, the balloon is actually attracted to the wall. So, and if you're wondering, Dr. Brenzi, maybe you didn't put it there, let me see if I can get it attracted to the wall. Let's see where it goes if I release it now. And there it goes into the wall. It's not very strong force, but it is attracted to the wall because when I let go, it goes, hey, you're not supposed to go that way. There we go. It goes into the wall. So something happened when I rubbed this balloon against this sweater. And it's not a force that we've seen before. It doesn't act like friction force, even though we've been rubbing one thing against another, and doesn't behave like any other force that we've seen before. Now, something really interesting happens when I decide to do this with two balloons. So let me reset my little simulator here, take my wall out, and add another balloon. Okay, so something really interesting happens here. So what I'm going to do is I am going to rub this balloon on the sweater just a little bit and then move it over here. And of course, that balloon wants to go back to the sweater every time I release it, like right now. Boop. And I'm going to take this balloon now, and I have a hold of it, and I'm going to rub it on the sweater a little bit and put it over here. Oh, it didn't do the same thing. So this blue balloon didn't get attracted. As a matter of fact, wait a minute, what's that balloon doing? Hold on, balloon. Let me see if I can get the yellow balloon to touch the blue one. Oh. Wait a minute. I actually managed to push the blue balloon away. So let's do this again. Let's take the yellow balloon. We know that if I let it go, it goes to the sweater. Now I'm going to grab the blue balloon, do a little bit of that same thing, and now my balloon is just drifting, but for some strange reason is drifting away from the sweater. Wait a minute. And that's even worse. Come on, balloon. Because if I try to get the yellow balloon to touch the blue balloon runs away like it has seen a ghost. So what in the world is going on here? Well, that's what a lot of physicists back in the 18th century thought when they first encountered this force. They were like wondering, what in the world is going on here? So they kind of had to get their brains together and just kind of say, okay, what are some properties of this force that we're dealing with here? And they came up with a couple of things here. Okay. So what they decided to do, they said, well, why don't we say that there are these things called charges? And let's say that if you have opposite charges, that let's say if you call one charge positive and the other charge negative, that something with a positive charge will attract itself to something with a negative charge. And let's say that likewise, if you have something that has a negative charge, and another thing with a negative charge, when you try to push them together, they will actually repel each other. So those were the rules for this new force, and they decided to call this, or eventually they came up to the conclusion that this is due to electricity. So this is what's called electric force. So these are rules for electric force. Opposite charges attract each other, and like charges repel each other. Somebody then came along. His name was Charles Augustin de Coulomb, French duke, or I don't know if he's a duke, but a French guy. He lived, in the 18th century, 1736 to 1806. So I'll just kind of give you an idea of when all this was going down physics-wise. And he came up with a law that would that you could actually use to calculate the amount of force between two objects that have this electric charge. And this is the formula he came up with. He said that the force due to electricity is equal to some constant K times the charge of one of your items times the charge of the other item. Whatever those two items are, we don't know. They could be a sweater and a balloon. They could be two balloons. And then you divide that by the square of the distance between them. Well, this force looks pretty familiar, doesn't it? I mean, if we just replace that with a big G, replace that with an M, and replace that with an M, that looks a heck of a lot like gravity, doesn't it? Well, they soon kind of realized that those two are, they have similarities. So we're going to actually talk about that but a little bit later. But back to Coulomb here. And so we call, in honor of Coulomb, who discovered this law, we call this constant K the Coulomb constant. And in SI units, it's equal to 8.99 times 10 to the 9. So there's another constant for us to memorize. In SI units, we measure charge in what are called coulombs in honor of Coulomb, who discovered this law. It's really difficult to kind of wrap your head around what exactly a Coulomb is without going a little bit more into electricity and the history of it. But I will define what a Coulomb is for you in terms of something that is more familiar to you. But I want to do that after talking a little bit more about this sweater and this balloon. Okay, so Coulomb discovered this law that says, okay, if we can actually calculate the force between two things that have electric charge. Now, there were a lot of advances made when people started in the early 20th century and maybe even the late 19th century, started thinking about what atoms are. We know that there was always this long time belief in science that there were, you could break down matter only so far, and then after a certain while, you couldn't break down matter anymore. And for a long time, even going back to the Greeks in ancient Greece, they actually came up with this name, the atom, and they figured out that, or they believed that this was a piece of matter that could no longer be broken down. Okay, so that's exactly what an atom means. So you learned from chemistry, and maybe even before that atoms are actually composed of subatomic particles. And we have inside what's called the nucleus of an atom, you have protons. Let's see if I don't know why I'm not writing here. Protons. Okay, so protons. And you have neutrons. And those reside in the nucleus of an atom. And then orbiting those neutrons and protons, or what's called the nucleus, are electrons. And soon after people started really being able to figure out that this is how an atom works, or this is what an atom is composed of, that we soon were able to actually figure out that these different subatomic particles actually have different charges. So an electron, we've discovered, actually has what Coulomb called a negative charge. A neutron is zero charge. Okay, it doesn't have a positive or a negative charge. It is neutral, and that's why we call it a neutron. And then protons have a positive charge. Okay. Oops, forget the parentheses right there. So, if I want to find out what the charge of an atom is, I can add up all the protons, and in this particular atom, there are 7 protons. Okay. So that would be a charge, let's say for now, we'll just call it +7. There are also, wait a minute, they're not 7. 1, 2, 3, 4, 5, 6. Oh, geez, I can't even count. Erase that. 6 protons. 6 protons in this atom. There are 6 neutrons, but they have 0 charge. So we don't, when we're calculating the charge of an atom, we don't even bother with the neutrons because they don't contribute any charge anyway. And then we want to count the number of electrons. So there are -6 electrons, or we could say -6 charges due to electrons. And what happens is that when you add all of these together, 6 plus -6, you will get 0 charge. Okay. In other words, most atoms that make up matter are neutral. Okay. They don't have a positive charge, they don't have a negative charge. Okay, well, that begs the question, well, why in the world do we have electric force if most atoms are neutral? Well, there actually is a way for things to get, charge, but actually now I need to talk to you about what those charges were. Sorry about that. I forgot that I had the slide in here. Okay, so I told you that an electron has a -1 charge and a proton has a +1 charge, but now I want to tell you about how these are connected with coulombs. So we used to have this unit way back in Coulomb's day, and they eventually named it after him, called a Coulomb, which is a unit of charge, but it's kind of a strange unit of charge. It's much better for us to, oh, hey, come back. It's much better for us to think about how much charge an electron has and how much charge a proton has. So an electron has a negative charge equal to -1.6 times 10 to the -19 coulombs. So that's, compared to a coulomb, that's a really, really small amount. And then a proton has a positive charge, and in terms of coulombs, that is going to be 1.6 times 10 to the -19, but that is going to be a positive number instead of a negative number. So when you are, so if I were to try to figure out what is the force between a proton and an electron, I would first have my constant K, and then for Q1, I would plug in the charge of an electron, which is -1.6 times 10 to the -19. And then for my second charge, I would plug in, let me use a different color here, I would plug in positive 1.6 times 10 to the negative 19. And then I would have to divide that by the distance between those two squared. Okay. More often than not, you're going to be dealing with charges of electrons and protons more than you're going to be dealing with charges of a Coulomb, 2 coulombs, 5 coulombs. So we need to get used to remembering that a unit of charge for an electron or a proton is 1.6 times 10 to the negative 19 coulombs. Okay, now that I've explained that, now let me tell you how things can get charged. Okay, how can things be positive or negative charged? Well, it turns out that in an atom, these electrons that are on the outer shell, I went and hit the wrong button. Okay, these electrons that are on the outer shell, these are the ones that are most susceptible to being removed from the atom. So sometimes what can happen is you can have an electron that goes missing. It can somehow be stripped away from this atom. Oh, and I touched sorry, I'm having all sorts of technical issues here. Touched my screen again. Okay, so once this electron goes missing, I now have plus 7 protons. Okay, and I'm not going to bother multiplying that times 1.6 times 10 to the negative 19. Sometimes it's better just to deal in units of protons and electrons. And now, oh, God, I did that plus 7 again. What is wrong with me? Plus 6, I'm sorry. So I have 6 protons. I have negative 5 electrons. So once this electron gets stripped, now I have a net charge of positive 1 charge. Okay. So if I were to express this in terms of coulombs, like if I had to use this in Coulomb's law, now I would say, okay, this Q is equal to plus 1 times 1.6 times 10 to the negative 19 coulombs. Okay. If I ended up with plus 2 for my charge here, then this number down here would be plus 2. And then I'd multiply that times 1.6 times 10 to the negative 19. Well, just like charges can be removed from an atom, sometimes you can get charges that get added to the outer orbit, or we call outer shell of an atom. So in this case, now I have plus 6 protons. Remember, we haven't changed the number of protons, unless you keep on making mistakes like me and think 7 instead of 6. But now we have negative 7 electrons. Okay, because I've added an extra electron to this atom. So I have a net charge of negative 1. Okay. And if I were to have to plug this into Coulomb's law, I would say that this has a charge equal to negative 1 times 1.6 times 10 to the negative 19. Okay. So this is how matter can get positively charged by losing an electron, or it can get negatively charged by gaining an electron. So how does this play into our sweater and balloon scenario? Well, let's go back to that simulation, but this time, let me reset it, and let me go back to the wall and just one balloon. Now this time what I'm going to do is I'm going to show you the actual charges. Okay, so, let me see, I got to do one more thing. Okay, whoop. Now, what you see over here is you might be able to see this, but these red marks are positive signs that represent positive charges, and then the negative signs, the blue symbols, represent negative charge. So most matter is neutral, which means there are enough electrons to, there's 1 electron per proton, and there's 0 net charge. But the rubber in the balloon has an interesting property that if you rub it against a material, certain materials, it will actually strip off the electrons from the sweater. So as I rub this balloon on the sweater, I now have lots and lots of negative charges, extra electrons on my balloon, and on the sweater I'm left with positive charges because the electrons have been stripped of those from those atoms, or an electron. I shouldn't say all the electrons, I should just say 1 electron. Okay, so once I release this balloon, let's remember that that opposite charges attract. So as soon as I release this balloon, like right now, this balloon is going to be attracted because it has a net negative charge. It's going to be attracted to the sweater that has a net positive charge. Now, an interesting thing also happens when I put this balloon on a wall. When I get close to the wall, the negative charge on the balloon actually pushes the electrons of the wall away from the balloon. So I have electrons, but all the electrons are over here. There's some here, but when you get down here, they're all scattered towards the wall on the right-hand side. They are like scared of the balloon. They're repelled by the balloon, so they don't want to be anywhere near that balloon. Okay. Well, what that does is that leaves a net positive charge on the wall next to the balloon, and since this is a net positive charge near the where the balloon is contacting, and there's a net negative charge here, opposite charges attract, so the balloon wants to stick to the wall. And if you're not convinced of that, I'm going to actually show you a demo of that in class tomorrow, just to prove to you that I'm not just like playing around with the simulator and tricking you. But then again, you probably already know, because maybe you've already done this. All right, so if I put 2 balloons in here, so let me reset this and go back to 2 balloons. All right, so both the balloons have a net 0 charge. The sweater has a net 0 charge, and of course, well, I took the wall out. So let me rub a little bit on the yellow balloon on the wall, or the sweater, excuse me. All right, and then let me also rub the blue balloon on there. Well, I didn't do it too well. Okay, wow, look at that. The blue balloon is already leaving. It doesn't like these electrons on the sweater. Now, just to be more convincing, let me do this one more time. So let me just rub a little bit on there. Okay, and then, of course, we see. Okay, oh, darn it, I can't do it that way. Let me try one more time. There we go, and then it attracts. Now let me take the blue balloon and swipe off the rest of those electrons. So now I have 2 balloons, and both these balloons are negatively charged. So this blue balloon, the closest thing to it is the negative charge of this yellow balloon, and this blue balloon wants to scatter. It doesn't want anything to do with the negative charges on the yellow balloon, and since that's the closest thing to the blue balloon, that's the charge that has the strongest amount of force on this balloon. And it gets even worse if I decide I'm going to try to take this yellow balloon and move it to the blue balloon. The blue balloon just wants to run away. So that's it. So this idea of charge explains very well what's going on with this mysterious force. So like charges repel each other, opposite charges attract one another, and then Mr. Coulomb said that there is a law where you can actually calculate the amount of force that 2 charges have on one another. I want to end this, and I know it's been long, but I think it's also kind of fun. I want to end this on a note comparing gravity with the electric force. Okay. So, go ahead and draw this Venn diagram. And we have, on the left-hand side, we have gravity, and we have the Newton's law of universal gravity, which we learned in Unit 6. And then we have, on the right-hand side, the electric force, the Coulomb's law, which we just learned. What do they have in common? Well, first of all, it's pretty easy to see that both of them have 1 over r squared. Okay, well, when a force is proportional to 1 over r squared, that means that the force is weaker as the distance between the two objects increases. So in terms of the distance between the two objects, these two forces behave exactly alike. When you have two charges close to each other, it behaves as though you have two masses close to each other. If you have two charges that are far away, the force is very weak, just like if you had two masses that are far away, the force is very weak. What are some of the differences between the two? Well, first of all, with force, or with gravity, excuse me, mass is what determines how strong the gravitational force is. As opposed to the electric force, where it is another property of matter, which we call charge, which determines the strength of the electric field, or the electric force, excuse me. There's another big difference, and that is that gravity is always negative. Okay, with you in the advanced class, I didn't introduce this negative sign in Unit 6, but I'm going to introduce it to you now because now I can put it in some context, because this negative sign actually means that the two forces are attracted to one another, or the two masses are attracted to one another. Well, with the electric force, we can actually have a force that is negative. Okay? If you visualize that one of these is positive and one of these negative, well, positive times negative gives me a negative force. So if I have opposite charges, they attract. And the way I can tell they attract with Coulomb's law is that if the force is negative. So the force can be negative, which means the charges are attracting one another. If the forces, or if the charges are like, in other words, positive and positive, well, positive times positive gives me positive, which means that my force is positive, and we know by observation that like charges will repel one another. So a positive force is repulsive. So the electric force can be positive, which means repulsive, or it can be attractive, which is negative. Whereas gravity is always an attractive force, which means it always has a negative sign. Okay, I know that was a lot of information to process, but I wanted you to get a good visual conception or concept about, how charge works. So, apologize for this video running long, but hopefully you'll come in tomorrow with either your memory refreshed or or educated about charge and electric force. And we're going to do some exercises on how to calculate electric force and charge, and we're actually going to finish with actually comparing how strong gravity is in comparison to this new electric force that we're dealing with. Well, until then, I hope you have a good evening, and I look forward to seeing you tomorrow. Bye.